The name of this section is partial derivative. Partial derivative is a generalization of the derivative that we were talking about for a function of one variable. So if we go back to the previous semester, let's call it point number 0, if we have a function f from R to R, we can consider the derivative denoted by f prime or df dx by the limit when we consider the function value at the new point x plus h minus the function value at the old point x denoted by h, divided by h, and the limit for h going to 0. If this limit exists, which is not always the case, then we call it the derivative at the point x. An example, if we have function fx, say x squared, then the derivative is 2x at the point x. And now if we have a function of more than one variable, let's consider a function of two variables. So point number 1. If we have a function f from R2 to R, then we can consider the partial derivative with respect to x or the partial derivative with respect to y. Partial means that we consider only a subset, a part, some small portion of the space of the arguments. And then prime is no more a good symbol to denote the derivative because it tells nothing about whether we choose to differentiate with respect to x or with respect to y. Then we use this notation, and to stress that it is a partial derivative, we write a different d. We use Deveron, which looks like number 6 in the mirror. df dx, and now again limit of h going to 0, a similar fraction like that. But this time, if we change the variables, if we change the arguments, we change x only to x plus h, and y is a constant for the moment. Divided by h. And similarly, we can differentiate with respect to y, and then we have the partial derivative of f with respect to y, which will be the limit, again for h going to 0. And this is a similar fraction, but this time x is a constant and y is changed by h. So x is always x, and y is shifted by h, and we subtract the old value of xy. Alternatively, we can consider a function g of x, which will be f at x for some constant chosen value of y, and then we can say that the partial derivative of f with respect to x is just the derivative of g. Now prime is a good symbol because g is just a function of a single variable. Or if we choose g to be, that was for df dx, and if we choose g as a function of y to be fxy, then we can define the partial derivative as g prime. Now x is a constant and y is the variable that is changed. So let's consider some examples. So these are just alternative approaches, alternative definitions of what is here. These are equivalent. So consider a function fxy being, say, x squared plus y cubed, then the partial derivative of f with respect to x is 2x. And if this is a constant, then the derivative of an additive constant is 0. And partial derivative of f with respect to y. Now, this is a constant, and this gives 3y squared. On the other hand, if we have a function that is a product of these two expressions, y squared times x squared times y cubed, then df dx will be 2x, and this is a multiplicative constant, so we multiply by this constant, and the derivative with respect to y, this is a constant, and derivative of y cubed is 3y squared. Alternative notation is f with the subscript x and fy. This is also a common symbol for the partial derivative. Well, and if the function is continuous and has continuous derivatives, we can consider the derivative of a derivative, higher order derivatives. And as always, defined by the limit, three possible outcomes. The limit exists and is finite, proper derivative, or the limit is in plus or minus infinity, improper derivative, and the limit does not exist. In engineering practice, we usually work with functions where the function and all the derivatives do exist and are continuous. So, let's consider this example, and we can consider higher order derivatives. So for this function, we can consider the derivative of the derivative. And at each step, we choose whether we differentiate with respect to x or y. So, for a function of two variables, we have two first-order derivatives. And then we have how many second-order derivatives? What do you think? Yeah, 4. We can consider the derivative of f with respect to x, and once again with respect to x, which is denoted by d2f dx2. And if we consider this function and differentiate once again with respect to x, we have 2y cubed. Or we can consider df dy and differentiate once again with respect to y, which is written d2f dy2. And this is x squared is a constant, and the derivative of 3y squared is 6y to the power of 1. But we can also consider the mixed second order derivative. We can consider the function df dx and differentiate with respect to y, which is d2f dy dx. And if we differentiate this with respect to y, we have 2x times 3y squared. Or we can take this derivative and we can differentiate with respect to x. Which is written d2f dx dy. And then we have 2x times 3y squared. Well, and as you can see, in this case, the mixed derivatives are equal. This is always the case under the assumption that the second order derivatives exist and are continuous. So if all the second order derivatives exist and are continuous, then these two are the same. But for other functions, they may be different. Also, this is the notation in many countries, in many languages, with one strange exception. In the Czech mathematical literature, the order is reversed. In this lower index notation, this would be fxx, this would be fyy, this would be fxy, and this would be fyx. So this is the definition and a few examples of partial derivative.